Welcome back, everyone. So we will continue the morning session with Shiraz Minwalla from CIFR. He will tell us about the Hilbert space of Chern-Simons matter theories. Go ahead, Shiraz.
Thank you very much. Thank you for the invitation to speak at this lovely workshop. I very much miss swimming in the lake, but next time. Okay, my talk today is titled The Hilbert Space of Chern-Simons Matter Theories, and is based largely on work to appear, hopefully very soon, and also on a lot of background material contained in all these papers. Okay, so let's start. My talk today will focus on three-dimensional gauge theories, particular kinds of three-dimensional gauge theories, namely gauge theories where the gauge self-coupling is governed by a Chern-Simons term. Okay. The field theory that we study will also have matter fields. So to start my talk, I'm going to give you some motivations for studying these theories. The first motivation is very simple. The Chern-Simons coupling is the most relevant operator that couples gauge dynamics. So if you've got a generic gauge theory in 3 dimensions with matter fields, it will generically be governed by a Chern-Simons theory in the infrared and sometimes by a Chern-Simons matter theory. That's enough motivation to study these theories as well as we can. A second motivation is that the Chern-Simons coupling 1 by E is the inverse of an integer, and so cannot continuously flow under the renormalization. This tells you that it's much easier to generate conformal dynamics, to make a conformal field theory using Chern-Simons theory than it is using, let's say, a Yang-Mills gauge theory. So it's very easy to generate conformal dynamics using Chern-Simons theory. That's another motivation to study these theories. A third motivation to study these theories is that they're unusual. They display physics of the sort that we don't easily encounter in other quantum field theories. For instance, particle-like excitations in these theories have non-half integer spins, sometimes obey anionic statistics, and have been shown to display unusual crossing behaviors in S matrices. Fourth, some of these theories have conjectured ADS-CFT dual descriptions. Fifth, and this was a post facto reason to study them, these theories, it turns out that these theories enjoy an interesting sort of Bose-Fermi duality, which will play a role in my talk. But from the point of view of my talk, perhaps the most important reason to study these theories is a technical one. The reason goes as follows. These theories have 2 interesting limits in which they become basically exactly solvable or basically tractable. And in these 2 limits, the theories don't completely trivialize. One limit is the limit in which the masses of all matter fields is taken to infinity. In this limit, the theory reduces to pure Chern-Simons theory, which is sort of a caricature of quantum field theory. It's a topological quantum field theory, but still sort of interesting. And this was an exactly solvable theory, which was solved by Witten almost 30 years ago. A second limit, which is sort of a bit newer, is the following. When the matter fields in these theories are the fundamental representation, and we take the Toft large n limit, so we take n to infinity, kappa to k to infinity, n by k or n by shifted k held fixed, these theories turn out also to be solvable, and yet continue to display reasonably interesting physics. Now, solvable theories are, of course, special. Solvable limits of theories are special. And it sometimes turns out that the Hilbert space of these theories has a very special structure. Sometimes, as I will try to convince you is the case in this theory, they're given by a sort of free Hilbert space with some sort of constraint. Okay. So in this talk, the purpose of this talk is to try to explain to you that the Hilbert space of these large n matter Chern-Simons theories is a very simple Hilbert space. It's almost a free Hilbert space with an interesting constraint to put on it. Now, the style of this talk will be as follows. By using path integral methods over the last 10 years or so, various groups with increasing sophistication have computed the path integral of matter Chern-Simons theories in this Toft large n limit. So the answers for the partition functions, the thermal partition functions on S2 times S1 certain circumstances, for the theories that we will be studying are known. The point of this talk will not be to find these answers. I'll just take the answers as given. The point will be to interpret these answers. So let's start. Before I start actually my talk, I need to tell you a little bit about the answers I'm going to try to interpret. Okay, so I'm going to be working in this limit. N goes to infinity, k goes to infinity, and also the volume of the two sphere goes to infinity, with all ratios of these quantities fixed, and all other quantities like masses and temperatures, chemical potentials, and so on held fixed. In this limit, at least, the answers to these thermal partition functions of Matter-Chern-Simons theories are well known. I'm going to tell you what is known from previous work about these answers. The first thing that comes out of calculation is the following. The S2 times S1 partition function of these Chern-Simons matter theories turns out to be an integral over a unitary matrix. This unitary matrix has an interpretation. It's the holonomy, more precisely, the zero mode of the holonomy on the sphere of this S2 times S1 path integral. And this integral over the unitary matrix comes with a certain action. I'll tell you more about the action in a moment. But on this slide, the thing I want you to focus on is that the measure for integration is slightly unusual. The measure for integration for this integral over the unitary matrix is the Haar measure, but with a constraint. You see, in the large N limit in which these answers have been deduced, you can rewrite a unitary matrix in terms of its eigenvalue density function defined here. And this measure for integration here is the usual Haar measure with one sort of weird element. The weird element is that we're only supposed to integrate over those unitary matrices whose eigenvalue density function pointwise never exceeds 1 over 2 pi mod lambda. Well, lambda was this Stoft coupling. Okay, so there's a sort of cutoff in the space of unitary matrices over which you're supposed to integrate. Okay, now to fully tell you about the answers, I have to tell you more about the integrand which is a function of unitary matrices. And to tell you about that, I have to introduce the theories which I will be studying. So the theories I will study are the so-called regular fermion theory, which is just a theory of free fermions, a theory of fermions that would have been free, except that it's minimally coupled to Chern-Simons coupled gauge. And the second theory in the same class, because these two theories are conjectured to be both Fermi dual to each other, is the theory of Wilson-Fisher bosons, ordinary large N Wilson-Fisher bosons that would have been these garden variety Wilson-Fisher bosons, except that they are minimally coupled to another Chern-Simons gauge theory. These two Chern-Simons gauge theories are sort of level rank dual to each other. More about that later. A second class of theories we'll be studying are so-called regular boson theories. So this is not a Wilson-Fisher boson, it's just an ordinary bosonic theory with some potential, and then gauged with respect to Chern-Simons theory. Okay. And the dual to this is what people sometimes call the critical fermion theory, which is this regular fermion theory coupled to a Lagrange multiplier that this regular fermion theory that couples to a Lagrange multiplier that couples psi bar psi with zeta. So Lagrange multiplier zeta couples to psi bar psi, and then a potential for the zeta. These two theories are also conjectured to be dual to each other. If you've not seen these theories before, you might have various worries about them. You might worry whether these theories are are stable, whether their effective potential could be unbounded from below, whether they're well defined, they follow from deformations of genuine fixed points of the renormalization group, and so on. All this has been studied at least in large N limit, and there are in the right range of parameters, there are no problems. Okay, so for each of the four classes of theories above, computation reveals that this quantity here, the quantity that appears as the integrand in this matrix integral, okay, computation reveals that the best way to present that integrand is sort of roundabout. And the roundabout way is as follows. Instead of just telling you about a function of u, it's better to tell you a function of a few extra parameters, zeta I and e. And the integrand itself is obtained by taking this function of these extra parameters, these auxiliary parameters, Lagrange multipliers sort of, and then extremizing over these extra parameters. Okay, so that's what comes out of computation. Now, so what I'm going to present for you is these so-called off-shelf free energies, whose extremization over auxiliary parameters gives you the integrand over u for this theory. Okay, and in the case of the regular fermion theory, it's given by this quantity. Here, C tilde F and C tilde CF and C tilde curly C tilde are auxiliary parameters, and rho is the eigenvalue density function of the matrix. So this function of auxiliary parameters and the eigenvalue density functions. And then there are similar such expressions for the other two theories. Okay, we don't really have the time to look at these expressions in much detail. The one thing I want you to notice is this, that let's say if we take the two fermions, there's a couple of lines in these theories which describe theory-specific kind of off-shell free energies. And then there is a third line here that is universal. That's the same for both fermionic theories, and in fact, independent of all the coupling constants in the fermionic theories. The same structure persists for bosons. There's some non-universal parts that really, as I will explain, describe the details of the contact interactions of the theories. And then there's a universal part that is the same for both bosonic theories. Okay, the non-universal part's a bit of a mess. The universal part is very simple. And we'll very quickly interpret this. Okay, so that was the structure of our, so let's summarize the structure of our S2 times S1 partition function from previous computation. Is the integral over a unitary matrix with this funny measure of an integrand. That integrand was given by extremizing an off-shell partition function over some auxiliary quantities. Now, in general, this is, if you had an expression of this form, this is all you could say. However, remember that these expressions were only valid in the large n limit. In that large n limit, this integral over u can also be performed in the saddle point approximation. And so it also reduces to some sort of extremization. So what are we doing here? Two extremizations. And so in the large n limit where these things were valid, you can equally well interchange the order of these two extremizations. In other words, you can interchange the order of this minimization and the integral over u. So this formula here can be rewritten in this form. Extremize over the auxiliary parameters of the integral over u of this quantity. Now, what's the advantage of this maneuver? The advantage of this maneuver was that, though you hardly had the time to see it, if you looked at the part of this free energy that depended on u, on these eigenvalue density functions, that all appeared in these universal lower lines here. Okay, and that was the sort of simple part of the theory. So this integral over u is universal and simple, and then everything sort of complicated goes into this extremization over zeta I, which can be done later. So the program of evaluating these partition functions can be split into two parts. First, evaluate this integral of u, which is a nice universal thing, and then extremize what you get over zeta, over these auxiliary parameters. So let's start with these two steps. Focusing on fermions for the moment. In step one, what we're asked to do is to evaluate the integral of u over this quantity. Now, for bosons, we're asked to do something very similar. The difference between fermions and bosons is that the bosons, in addition to having this nice looking sum of logs, which are very familiar and we'll very soon interpret, also has this very odd theta function piece, a piece that kicks in only when the chemical potential of the theory is larger than the CB, which, as we will see, is the interpretation of a mass, the thermal mass of the bosonic particle. So it's the kind of thing that comes in when the bosons want to Bose-compensate. So the fermions are simple. Let's first suppose that we've managed somehow to evaluate these IF and IB. Then what do we have to do to evaluate the full partition function? Well, what we have to do is to dress this IB, let's say for the bosonic case, with the remaining dependence on these auxiliary parameters, and then extremize the product of these two over CB, sigma, and S in this particular case for the RB theory, the regular boson theory. Extremize over these parameters. Okay. Now, just for this one particular case, the case of the regular boson theory, I'm going to just take you through this for 2 minutes. Extremizing this quantity here over S is very simple, because S appears here as a quadratic and a cubic piece, and its equation of motion has two solutions. It's a quadratic equation which has two solutions. This is the equation of motion. The simpler of the two solutions is just that S is equal to minus sigma B. Turns out that these two solutions define different phases of this regular boson theory. One in which it's unhiggsed, that's the solution with S is equal to minus sigma B. And one in which it's higgsed. We won't in detail study that in this talk. In the unhinged phase, S plus sigma b is just 0, so these two terms just drop out. Okay, and so in the unhinged phase, this ZRB is just this quantity. Oops, this shouldn't be an extremization over S anymore, just over sigma b of this thing. Now, I want to show you another problem that has a very similar structure. Suppose you just had an ungauged scalar large N matter theory whose Lagrangian was chosen to take the following, form. Okay. It's actually the Lagrangian here turns out to be that we need to use for what I'm going to say, turns out to be the exact quantum effective action of the regular boson theory as a function of psi bar psi. So there's a rationale for choosing this particular Lagrangian. But at the moment, we've just chosen another theory, no gauging. We've got this Lagrangian. Now, if we were trying to solve this ungauged theory in the large N limit, it's almost trivial. With the aid of Lagrange multipliers that sort of set a Lagrange multiplier that sets sigma to phi bar phi with some normalization. That Lagrange multiplier that sets that. So the two additional Lagrange multipliers, sigma and CB. CB, the equation of motion for CB is that sigma is phi bar phi with some normalization. Then the equation of motion of sigma is something else, which doesn't matter. This Lagrangian here can be rewritten in this form, where all the interaction terms have been rewritten as interactions for this Lagrange multiplier sigma. And the dependence of the action on phi is now quadratic, and it's very simple. CB will eventually be determined by an extremization. We assume this extremization is translationally invariant. Then CB is some constant. It's not a field; it's just some constant number. And we can evaluate the path integral of this, the path integral over phi to obtain this partition function, which is just the partition function of a bosonic field of mass CB dressed by these Lagrange multiplier factors. Okay, and then extremized over CB and sigma. So what this is some sort of transform of the usual free boson Fock space partition function, transformed because CB appears both here as well as here. Some sort of transform, a little bit like a Legendre transform of this of the free Fock space answer. This is the standard answer for the thermodynamics of these ungauged large N matter Chern-Simons theories. They're very close to being free theories, but then there's this additional transform which takes into account the effect of forward scattering interactions in these theories. What we see for our gauged theory is that we've chosen this corresponding ungauged theory to have the Lagrangian so that we get exactly the same dressing, except that the trace over the Hilbert space, the Fock space, is replaced by this other stranger quantity IB. IB was this thing that we talked about, this strange integral over the unitary matrix of something. Okay, so IB plays the same role for the gauged theories as the trace over free Fock space plays for the ungauged theories. Okay, fine. Now let's look at IB and IF. Okay, let's look at IB and IF. IB and IF were these quantities. I'm going to start with the fermions. So let us first start. The fermions went this way. Okay, it's not difficult to check that the integrand that appears for the fermions is simply the twisted partition function over a Fock space, twisted by the unitary matrix U. So treat these fermions as having an UNF global symmetry, twist with the unitary matrix for that global symmetry, and compute the partition function over free Fock space. That is the integrand for these fermions. So all we need to do is to compute IF, which is this integral over the Chern-Simons modified measure, Haar measure of the twisted partition function of fermions twisted by U. Now recall that something similar happens for bosons, except that there's this additional strange theta function factor. Now, in order to understand what's going on here, recall the following. Okay, if we were for a moment just to consider a toy model for what we wanted to do, replace this Chern-Simons modified measure with the usual Haar measure, then this integral over the usual Haar measure of the twisted partition function of free fermions has a very simple interpretation. It's simply the projection of the free fermion Hilbert space, a partition function over the projection of the free fermion Hilbert space onto its SUNF invariant subset. That's what I've written here on this in the slide. Question: if we do what we actually need to do, have the strange measure, is there a similar interpretation? Okay. Answer: yes. Both the integrals that I presented to you have some sort of similar interpretation. But the correct interpretation is going to be that instead of projecting down to just the group theory, SUN invariant sector, what this funny modified integral over U does is project down to the space, the subsector defined by the space of Witten singlets. Okay. In order to see how and why this is true, I need to take you through 5 minutes of technicalities. In this talk, I will be interested in SUN K Chern-Simons theories and the Witten duals, as well as UN KK prime Chern-Simons theories. Roughly speaking, UN theories require 2 levels because roughly speaking, there's a level for the SUN part and a level for the U1 part. Because UN is not quite SUN times U1, these 2 levels are not completely unrelated. In fact, the consistency demands that the level for the U1 part K prime differs from the shifted level of the SUN part by an integer times n. Okay, we need to consider both kinds of theories since all level rank dualities sort of mix them up. We could have considered just the UN KK prime theories. We can't get away by looking at just the SUN theories. Okay, now suppose we had one of these kinds of these Chern-Simons theories, and we studied the S2 times S1 partition function of this theories with the insertion of M Wilson lines. These Wilson lines are points of the S2 and are wrapping the S1 circles in representations R1, R2 up to Rn. You can ask as a question, what is the partition function of pure Chern-Simons theory with these Wilson lines inserted in these representations? It doesn't matter where they inserted because this theory is topological. Well, over 30 years ago, Witten famously demonstrated that this path integral generates the dimension of the space of conformal blocks of Witten theory, whose primary fields are in representations R1, R2 up to Rn. Okay. So now this space of conformal blocks, the dimension of the space of conformal blocks can be computed in many ways. One way is by using the Wallende formula. Another way is by using direct path integral evaluation. All ways should give the same answer if you do them carefully. We were actually not able to get exactly the same answer from the path integral evaluation, the Wallende formula, because of some detail, which anyway, we're pretty sure what the right answer is. The Wallende formula is unambiguous. And for instance, for SUNK theory, you can take the Wallende formula, which is often written in a sort of complicated form, and massage it in this particular case. Something quite simple looking. The number of singlets, the dimension of the space of conformal blocks is given by summing over a bunch of distinct eigenvalue configurations of the SUN holonomy and then some integrand. So the integrand is just the Haar, effectively the Haar measure. So I'm now working on S2. Yeah. So the integrand is effectively the Haar measure times the characters evaluated on these eigenvalues. The solution set over which you have to sum is sort of interesting. Each of these Wi's are eigenvalues of the SUN matrix. It's an SUN matrix, so the product over Wi's is 1 and mod of Wi is 1. The phases. Okay. What's sort of important is that these eigenvalues also require to satisfy a condition, an equation. The equation is that Wi to the kappa is equal to Wj to the kappa for all kappa. Now, it's not difficult to convince yourself that there's a finite number of solutions to these equations. You're supposed to sum this quantity over each of these finite number of solutions. And when you do that, you get the number of conformal blocks. Similarly, in the case of the UN KK prime theory, there's a similar formula with similar structure, slightly different equations. Okay. And in the particular case of the UN KK prime theory with K prime equals kappa, so the case Q equals 0, the formula sort of really simplifies very much and often for illustrative purposes. This is the case of what I call the type 1 UNK theory. The formula simplifies to this sort of nicer looking expression, and the equations that the eigenvalues have to satisfy just become the condition that each eigenvalue has to be in a kappath root of either unity if n is odd or kappath root of -1 if n is even. Okay. Now, so this is this formula that tells you. So this was just some background. Some of you are wondering why I'm telling you about this, but it's going to matter. This is the formula that tells you how many quantum singlets, how many conformal blocks you have with these insertions. Now, what happens to this formula in the large n limit? Well, in the large n limit, you see this measure here is basically the Haar measure. In the large n limit, the set of all possible kappath roots of, let's say, unity are very finely spaced, because in the large n limit, kappa also goes to infinity. So this becomes a particular discretization of the Weil integral formula that counts the number of classical group theory singlets in the tensor product of R1, R2, R3 up to Rn. You might think that it becomes exact in the large n limit. This discretization goes over to the integral, becomes exactly the integral, but that's not quite the case. It's not quite the case because you see, two eigenvalues can't be equal to each other, and there's a minimum spacing between these eigenvalues. When you translate that condition to it becomes a condition on an upper bound on the density of these eigenvalues. This density of the eigenvalues cannot exceed 2 pi by lambda. So in other words, this formula in the large n limit becomes an integral over the Haar measure, but with the constraint on unitary matrices that we were calling DUCS. Okay, so in equations, this discrete sum in the large n limit becomes the kind of thing that we were interested in. And then when you use that, you can easily convince yourself that that fermionic partition function IF was simply the restriction of the partition function over the restriction of fermions to the Westermino-Witten singlet sector for free fermions. Now that's great, but bosons weren't this simple, right? There was this additional theta function term. How does that work? Well, turns out that it works very beautifully. Now, see, if we were to do the same thing for bosons, we would just look at the twisted bosonic partition function, which if we were to look at just the twisted bosonic partition function and restrict that to the space of Westermino-Witten singlets, okay, we have to do this carefully. The reason for that is that if you take any single particle, any single energy eigenstate partition function for bosons and expand it in number of occupations of bosons, the number of occupations runs off to infinity. Because bosons obey both statistics. If the occupation number in a particular state is n, then the unitary matrix dependence of that sector is in the symmetric product of the representation whose Young tableau has n boxes in the first row. Okay, the symmetrized product of n fundamentals. Now, the partition function over these bosons. Okay, if we were really wanted to restrict to Westermino-Witten singlets or to the space of conformal blocks, there's an important point here, and the important point is this: Gepner and Witten showed long ago that if you have a bunch of integrable representations, that's say one or more non-integrable representations, then the conformal blocks coupling these two vanish. Non-integrable representations in Westermino-Witten theory decouple from the integrable representations. Now, when n exceeds kappa b, this is the character of a non-integrable representation. So what we're supposed to do is to take this sum, truncate it at kb, and then put that back into the Wallende formula. Okay, so this is the correct thing that we're supposed to do. We're supposed to put it in the Wallende formula with each of these factors replaced by a truncation up to kb. And when you work through what that does in the large n limit, it gives you exactly a bosonic kind of partition function, but with an extra piece. And that extra piece is that theta function term. Let me explain to you sort of how that happens. Why the theta function comes about. A theta function comes about because, you can truncate, you can enforce the truncation by looking at an untruncated denominator and then multiplying by a factor that would kill the extra terms. So the additional thing that you get is a log of the usual kind of bosonic form, plus an additional log that, this should have had a -1 to the power, plus an additional log that accounts for this compensating factor that enforces the truncation. Now, in the large n limit, kappa goes to infinity. So if y is less than 1, this additional log doesn't matter. But y was e to the power minus beta into e minus mu. So y is less than 1 if the energy is less than the if the chemical potential is less than the energy. And that always happens for every state if the mass of your particle is smaller than the chemical is larger than the chemical potential. On the other hand, when the chemical potential becomes larger than the mass, there are some states in which y is greater than 1. This formula, this thing kicks in, gives you this additional term, and adding that up for all states gives you the theta function term with all coefficients, exactly right, that we talked about before. So we've learned something important here. If we take these large n Chern-Simons matter theories, no single particle state, bosonic state, can be occupied more than kb times. We call this the bosonic exclusion principle. It's the direct level rank dual of the more obvious result for fermionic theories, namely that no single particle fermionic state can be occupied more than nf times. Now, this has, of course, important physical consequences. Recall that a free bosonic theory is ill-defined at values of the chemical potential larger than the mass of the theory, just because states with energy lower than the chemical potential want to be infinitely occupied, because the Boltzmann suppression factor becomes a Boltzmann enhancement factor for such states. Okay, the bosonic exclusion principle stops this runaway. Things don't want to be infinitely occupied; they want to be occupied up to kb. Okay, so this is these theories don't have the runaway instability for Bose condensation that we see in free bosonic theories, and it's a very particular and beautiful way of curing this. Okay, so to recap, the partition function of large n matter Chern-Simons theories is given by an expression of the same form of the ungauged counterparts, the stressing times something, except that the role that was played by the partition function, the simple partition function over Fock space in the ungauged theory, is replaced by the partition function over Fock space truncated to the Wess-Zumino-Witten singlet sector in the gauge theory. Okay, now this statement becomes particularly interesting in the limit that the volume of the sphere is taken to infinity. You see, in imposing this Wess-Zumino-Witten condition, what we were supposed to do is to sum over all eigenvalue configurations. But in the limit that the sphere size goes to infinity, the different contributions are have infinite ratios with each other. So the full answer is given by the leading contribution. And the leading contribution turns out to be the contribution where the eigenvalues are of this for the matrix where the eigenvalues of this form. Actually, it works out very beautifully. This is exactly right, both for SUN and UN KK prime theories. Because of that, our formula no longer has a sum. Our formula for IB no longer has a sum. It's just a product of terms. And so up to in a proportionality, the partition function in this large sphere limit becomes the product of partition functions, one for each single particle state, one for each single particle energy eigenstate. However, the single particle energy eigenstates, their partition functions are different from what they would have been for either real bosons or real fermions. And the way the difference goes is as follows. For instance, I've written it down here for the bosons. Whereas for bosons, you would have had these combinatorial factors that I presented to you before. In these theories, what happens is that the combinatorial factors are replaced by their Q number analogs. Similar expressions for bosons, fermions. So ignoring details for the moment, an immediately striking aspect of this large volume limit is that the partition function factorizes as a product of partition functions, one for each single particle state. Now, this is really striking, right? Because usually when a partition function factorizes over different elements, it's because the different parts are not talking to each other. Yet we see that's not the case here, because the reason that we've got a different partition function in the gauged and the ungauged theories is that this overall singlet condition is coupling the whole system. Nonetheless, we get this factorized form of the partition function. The reason for this goes as follows. There's an interesting fact about Wess-Zumino-Witten fusion rules. The fact is that if you take a large number of representations, put them together and fuse them, and ask how many of these representations on the singlet, how many of these on the first integrable representation, how many in the second, and so on. Let's call these numbers n of Ri. Okay. in the limit where the number of representations that you fuse goes to infinity with n and k held fixed. Turns out you can show, maybe show is a bit exaggerated, at least we can give a physicist type argument for the following claim, that the ratio between the number of Ri to Rj's becomes something universal, and in fact is equal to the ratio of the quantum dimensions of these two representations. Now, the universality of this fact explains this factorized partition function. In a way I could explain to you, but I think I'm running out of time, so I'll skip that. So that the factorization is not a statement about the various states not being coupled. It's in fact a statement that they're coupled, but in a sort of very universal way. So the coupling between what's happening with all the other states of this one state is insensitive to the details of what's happening in the other states. That's what the universality ensures. Okay, very good. Now,
how much more time do you need, Shiraz?
2 minutes. Sorry, Sean.
Perfect.
Yes. Sorry. Okay, so recall that I've told you that these single particle partition functions take this following form. Now, the one thing I wanted to tell you is that this single particle partition function, sort of in the limit that we keep, take kappa large and vary NB. In this limit, if we vary NB, we start from, if NB is small and kappa is large, this partition function becomes that of free bosons. But in the other limit, where KB is small and kappa is large, this partition function becomes that of free fermions. In fact, here it's a partition function of NB free bosons, where it's a partition function of KB free fermions. In the middle, it's neither. So this single particle partition function defines a new statistics, one that interpolates between free boson and free fermion statistics. Okay, so it's sort of a one parameter deformation between free boson and free fermion statistics that interpolates between the two. Okay, fine. Let me just skip the rest. We can talk a little bit about the energy renormalizations because of this the stuff from extremizing the auxiliary parameters. All that I want to say is that that you see those things are the same in gauged and ungauged theories. See, now when you take a theory of matter stuff coupled to gauge, a couple of these gauge bosons, you integrate out the gauge bosons. You're generating what looks like very non-local interactions between these matter particles. One way of understanding what I've tried to explain to you is that the only effect of these non-local interactions, as far as the partition function is concerned, is to impose this Weissumino with singlet structure condition on the Hilbert space. Okay, so I'm done. These are my conclusions and future directions. I'll put them up and stop. Sorry for going over it.
Questions? Maybe from the audience and from home. Is there any question from Zoom?
Hi, Shiraz.
Hi.
What was you said that the effective number of states of each of the of these different anionic types did not have to be an integer. Is that right?
Yeah. Okay. Good. Excellent.
What determined this number of states?
Excellent. Let me tell you a little bit. Okay. So this is let's take this the bosonic Q modified bosonic single particle partition function. Okay. This quantity here is not the partition function of an independently well-defined Hilbert space. And you can see that from the fact that, as you point out, these coefficients here are not integers. When Q goes to 1, these are, of course, integers. But the Q versions of these are not integers. They're real numbers. In fact, for every Q less than 1, they're less than the integer values that you get at Q equals 1. Okay. Now, you can ask why. This is the point. You see, the point is that it's not that we've got a new free theory where there is a Hilbert space associated with state 1, a Hilbert space associated with state 2, and so on. That was the case for free bosons. It was the case for free fermions, but it's not the case for this theory. In this theory, the partition function becomes a factorized product of partition functions over individual single particle partition functions, even though the Hilbert space is not a factorized product of Hilbert spaces. Okay, and let me explain to you how that comes about, since you asked. You see, this universal feature of the representation theory of Westerby-Witten theory tells you the following. Suppose I take any one single particle state and take all the rest of them and call that C. In the large volume limit, the C has an infinite number of states occupied, a very large number of states occupied. So this rule works for the C. Now, the number of states that you get from your single particle, if you put n particles in your single particle, your one special single particle state, is the number of ways you can make singlets where the guy where you put these n particles is in the n box symmetric representation. And then you have to couple that to the C to get a singlet. But the only way you can couple the C to get a singlet if you start with an n box symmetric representation is to take its conjugate representation. So the number of the number of states that appears is the number of conjugate representations to the n box symmetric that appears in the full fusion of the C. But that's given by this formula. Yeah? And that's why this dimension, this quantum dimension, this Q deformed number appears. Okay, so this number is a consequence of counting numbers of singlets. It's not the number of states that were there in the single particle state. It's not like it's a product of Hilbert spaces, one for each single particle state. Okay, it's coming from a non-trivial projection. What's incredible is that this projection nonetheless leaves the product structure intact because of this universality. The universality is a consequence of the fact that, you see, no matter what is happening in the C, it doesn't matter. This ratio always remains the same. And that gives this product structure. Sorry, I hope that answered your question. Please ask again.
Yeah, I think it did. I presume it means that the typical the dominant contribution from this product is one which has large enough occupation number from many of them so that it sort of all fits together. Because in the total answer, you would have integer coefficient.
Yeah, the total answer is an integer.
Okay.
Right, exactly. Right.
Kind of like the integers come from fractionalizing into like anyons in a sense. Is there a picture like that that makes sense?
I don't have a picture along the lines that you're talking about. Maybe there is some dual way of thinking of it like that. Here it's just coming from the singlet condition. Now,
yeah, I understand.
Yeah, it would be great if I had something more dynamic to say. I don't have anything to say. Thank you. Thank you for the question.
More questions? Okay, if not, let's thank Shiraz again.
Sorry for going over time again, Joao.